All right, so let's continue on with this control volume method. Last time we found Fick's second law, and so we want to go ahead and continue on with that. All right, we applied the experimental conditions, dc dt is equal to 0. We got our governing equation of 0 is equal to the second derivative of c with respect to x. And this was an ordinary differential equation. Okay, we saw that last time in the previous video. So we're going to take this equation now and we're going to go ahead and solve that. I've written out all the steps here, even though I know this is a relatively simple equation. Okay, but one way to do it is to take the second derivative and rewrite that again as the derivative of the first. And then we can move the dx over. And so we have the integral here really of 0 dx. And we have the integral then of d of dc dx. So the integral of the full differential is just the stuff inside up to a constant. Okay. And so we have dc dx coming out, and we have a constant. So this is our constant of integration. You don't really need this step. This could just be 0 here. And when you do this one, you get a constant that you move over to the other side. We have b1 as our constant. All right, so what we're going to do now is to put the dx over to this side and then integrate both sides again. So integral of dc is just c. The integral of b1 dx would be just b1x. And then again, we have an integration constant. So we get c is equal to b1 times x plus b2. So that is our equation, that is our solution for this general differential equation that we found last time. So we can already see we've proved that the concentration is linear across a thin membrane in steady state. Right? Here's the concentration, and it's given by the equation for a line, right? mx plus b. So slope of the line, intercept. And so now all we have to do is to go ahead and solve for the b1 and b2, and then we will get an equation for the concentration as a function of position as I move from the left side of our membrane to the right side. Okay, so we're going to apply the boundary conditions. So we're going to take that equation, move it on up, and we're going to go ahead and define our boundaries. So at the left side of the problem, so x equals 0, we're going to have a high pressure concentration. And at the right side, which would be x equal to delta, because we said this was the film thickness, we're going to have a low pressure concentration. Those are fixed at those two surfaces across our membrane, x equals 0, x equals delta. And so we can go ahead and use that information and plug back into our equation up here. So we can go ahead and put in C is equal to the high pressure concentration when x is equal to 0. So there it is. And we can put in when x is equal to delta, C is now equal to C on the low pressure. So here's that equation. And then we just have to solve these two for the constants b1 and b2. Okay. So this equation, this one falls out, so we see b2 is equal to the high pressure concentration. And then I can take that value and put it in here for the second equation, and then rearrange and solve now for b1, and I'll get low pressure minus high pressure over delta. So those are our two integration constants, which now go back in to this equation here. So I'm going to put this in for b2 and put all of this in for b1, and I get my final form of the equation. The concentration is equal to the low pressure minus high pressure divided by delta. That's the slope term, right? And we saw that that was actually linear now. We used this before in Fick's first law. Okay, that's the slope. And then the intercept on the left side is the high pressure concentration. That's just how we set the problem up. So if x equals 0, I get C is equal to the high pressure. If X is equal to delta, then these two cancel out and I get C is equal to the low pressure. And so everything seems to be working, and I have my final form of my equation. Okay, so next time we're going to do take a look at this solution and just make some observations and some conclusions. All right, so I forgot I had slides here showing you the sketch of this. Let's keep going. So here's my equation again. This was my setup, my sketch of this problem in your textbook. So this was the high pressure value and the low pressure value. And then we put a linear line across here. This is what we assumed. Now we see that that indeed is true. So if I put in the values for the low pressure and high pressure that are given in my film thickness, I'm going to get my equation. And then if I just go ahead and actually put some axes on here, then I can go ahead and plot my equation. There it is. So when we draw these axes, we usually don't put these on here. We kind of assume they're there, but this is what we mean when we're drawing across here a concentration profile. We sort of pretend that we've got an x-axis defined here pointing to the right, and that's the positive direction. And then what we're plotting is ultimately concentration. Okay, so again, the slope here is 2100, negative 2100, right? Negative slope. And the intercept up here is 2.2. All right, and that is our problem. And when we go ahead and solve for the flux, we will see that the flux is a positive quantity, meaning that it's pointing to the right, into the positive x direction. And that's what we know to be true because the flux will move down the concentration gradient from high pressure to low.